Consider all right circular cylinders for which the sum of the height and circumference is 30 centimeters. What is the radius of the one with maximum volume? The minute you see the word maximum in here, think to yourself, optimization. We want to optimize the volume. We want to find the maximum volume. Well, let's create a model for volume. The volume of a right circular cylinder is pi r squared times h. Now, we have two variables in our model. We have both r and h. When we do our first derivative analysis to determine the relative max, we're going to take the derivative of volume with respect to either radius or height, but not both. So we have to get volume in terms of only one variable. Luckily, they've given us some more information, which is that the sum of the height and the circumference is 30. That means that the height plus the circumference, and the circumference of this cylinder is 2 pi r, is equal to 30. Well, which variable would be easier to solve for? Probably h. So h is equal to 30 minus 2 pi r. This means that we can now substitute 30 minus 2 pi r into h. And that will give us volume in terms of only one variable. So here we go. The volume is equal to pi r squared times h, and h is just 30 minus 2 pi r. Let's distribute. V is equal to 30 pi r squared minus 2 pi squared r cubed. Now, we need to take the derivative of v. So dv dr is equal to, the derivative of 30 pi r squared is 60 pi r. The derivative of negative 2 pi squared r cubed is negative 6 pi squared r squared. And now let's find the critical points of v. We'll do this by setting dv dr equal to 0. Because this is existent everywhere, the only place where we might have possible critical points are when it's equal to 0. Let's factor here. We can take out a 6 pi r, and what's left over is 10 minus pi r, and this is equal to 0. This means that either r is equal to 0 or 10 minus pi r is equal to 0. We can subtract 10, divide by negative pi, and r is equal to 10 over pi. So we have two critical points, one at r equals 0 and one at r equals 10 over pi. Now in context with this problem, the radius being 0 makes no sense. So we'll get rid of that one. R equals 10 over pi, that's fine. That seems reasonable. So let's do our first derivative line analysis on v prime. So here is 10 over pi. Let's look to the left of 10 over pi, but to the right of r equals 0. We'll keep that over here just to remind ourselves that we can't go further than that. Well, pi is about 3.14, and 10 over that will be more than 1. So probably 1 is going to be a good guess for something to the left of 10 over pi. If we plug 1 in, we have positive on the outside, and 10 minus pi is positive on the inside. So this is positive right here. To the right of 10 over pi, let's just try 10. Positive out here, and inside 10 minus, oh, that's going to be huge. So this will be negative over there. Which means that we have a relative max at r equals 10 over pi. And the question was, what is the radius of the one with maximum volume? Well, we just figured it out. This is the radius right here. The radius that maximizes the volume is 10 over pi. And that is our answer.